Hi, everybody. Professor Z here with your introduction video to week one. Um, I usually like to, give some sort of overview of the topics that we're going to be talking about or the content of this week. And so, what I thought was I'd do a short introduction video, relatively short. You may not think it's short, and excuse me. And we'll probably well, I definitely will be. You'll see here in the index, there's other videos to follow that are going to be specific problems that, or examples of problems that you're going to be working in, Alex. So to get started here, just to introduce the topic here again, statistics. What is statistics? I'll get into this slide here in a second, but with this being a non-traditional course, we're going to, get through it in 7 weeks, which is pretty quick. And so I opened your book, your textbook, which I know math textbooks are always a favorite to read. And but I will try to have a little bit of humor here. But anyway, I just wanted to point out that if you go through the table of contents here, the content we're going to cover actually goes over chapters one, which is essentially, some of the stuff I'm going to talk about here, but also how to collect data and different variables, frequency distributions in chapter two. And this will be, again, kind of, the whole thing about how to do graphs and make graphs and so forth. And then how to describe data with measurements and statistics, if you will. We'll get into that. So what I'm trying to say is that, that's 3 chapters of your textbook, and that's going to be the content of week one. So um, obviously there's a lot of stuff in this textbook that we're not going to be directly coming in contact with. Like I said, it's an abbreviated course to some degree, but you will see that, a lot of this stuff here is going to pop up, but not all of it. So to get on with this, what is statistics? And, I have here, there's a bunch of definitions and so forth, but, basically what we do is it's a science of reasoning from data. It's a systematic way of collecting data to essentially make decisions. Okay, so use that data to make decisions. And so that's, what hopefully you're going to find out is that happens. Quite a bit throughout the day that you'll encounter at least some sort of, uh, result of some sort of statistical study or process and so forth. So, as we get through some examples, I think you'll see that as we go through. But essentially, that's just, there's some problem out there. We collect data and we use that data to answer questions or to solve those problems. And so, what we're again going to get into essentially this first um, week is actually the 2 major areas where we're just going to be describing data. So, we'll take a look at, what a sample is here in the context of maybe an example in a population, what that is. And, but essentially we're going to get a bunch of numbers or a bunch of responses in a survey or something like that. And then we're going to try to, again, put it in an organized fashion to kind of make some sort of conclusions that would be obviously going to be informal due to the fact that, those types of conclusions only apply to the data that we collect. However, if we go about this in the right way and collect data, which, and I just have this here in data production, that's good or representative or have a sound or well-designed experiment, what we can do is we can base our conclusions, these conclusions we have with the data are telling us to an entire group of people. And, it's typically impractical to collect, let's say, just example, presidential elections coming up, presidential polls. We don't have time to ask everybody who they're going to vote for. It just would be very impractical and, logistically, essentially very difficult to do. And we know what it takes just to run an election. That would be almost running the election. And so what we do is we ask about 1,000 people or so, plus or minus, and based on that response, we have a pretty good idea of how the entire group's going to respond to it. But in order to do that, and by the way, that is inferential statistics, we're going to draw conclusions about a population based on just a small portion of what we find out of that small portion or the sample of that population. And if we do this in the right way and get data that are representative of the whole group, all right, if that's done correctly, and or we run a good experiment that again produces data that would be representative of the entire population, then we can draw conclusions about that population. But again, because we have just a small portion of it, we still have that, in the back of our mind, that chance of, well, what if they're not representative? And a lot of times we don't know that. And so we have to just rely and trust that our methods that we're using, which typically do present data in a representative form, are going to be applied. And if we do that, then we can use probability to kind of have some sort of level of confidence or certainty about these conclusions. But again, they're going to be based on probability. So that's essentially, everything here of what statistics is all about and what we do. What we're going to get into are actually the methods. And again, there's a bunch of them. And it again depends on the type of question and how many populations we're examining and what we're comparing. So as we go through the course, we're going to spend most of our time in this realm of inferential statistics. Okay, to go ahead and because that's essentially why you're taking this course, to have that background and understand how that works. From what I understand, a lot of nursing majors take this class, and so even though you're not a researcher, you're going to be using, methods and or medications, again, that have been vetted by this statistical process as being best practice. And so to have an understanding of how that works, how that vetting works, and those decisions are made of what to do and what not to do, that's why you're taking this course. Me being, I guess I'm like right at the end of the boomer generation. So I was born in 64. So when I started taking classes, and actually when I started teaching, computers and software weren't widely or readily available. It was still in developmental stages back in the early 1990s. And so I kind of look at myself as fortunate, seeing what statistics was in the past and the impact of technology on it. It's made it much more, accessible to the normal person, because in the past, everything was focused on how to perform calculations and how to construct graphs and all this sort of thing. It was very process oriented, and people got lost in the weeds, getting so bogged down into doing this, they really never understood how to apply it or why they were doing it. Whereas now, if we can give all of this stuff, constructing graphs and performing calculations, and let the technology do that for us, then what we can focus on is how to interpret those graphs and how to interpret the results of the calculations. And so, like I said, I taught a stats course back in 1990. And it was pretty much just that. Everything to, we still had calculators, but again, no software, and those calculations were very tedious, and used rulers and graph paper to make graphs and so forth. And now it's just a couple of clicks and drags and whatever we do on a computer, and it's going to happen. So, all right, so don't want to get too bogged down in that. So all right, so we're going to be collecting data. And what is data? Well, data again is just the values of these variables that are assigned to subjects. And you're going to get into some of this and some of your content and Alex. There'll be some questions and content that you can get into. So this isn't exclusive. I'm just trying to hit the main points here. But when we collect data, let's say if we do a survey, we ask them a question. The answer to that question might be yes or no. That is the data point, or the datum is the singular form of the word. And so what we do is we've got a bunch of stuff that are qualitative of nature. It's either yes or no. If I ask the question, what's your favorite color, red, blue, or yellow, and people had to choose one of those three, again, the response is a color. So we talk about that being qualitative and categorical in a sense, where we can't like calculate the average color or do any type of calculation with it. But what we can do is count those things, count the number of people that said yes, count the number of people that said no, and so forth. So there's a whole realm of methods that we can apply to data like that, okay, qualitative or categorical data, where we focus on the count. This is in opposition, or I guess in contrast to uh, quantitative data. And what quantitative data is basically some sort of number that we're going to collect. How tall are you? How much do you weigh? What's your shoe size? How much money do you make in a year? So forth. And so when we do that now, what we get into is this idea of measuring. Okay, whether we ask them a question, we can measure how tall they are with some sort of measuring implements. We can measure how long it takes to do a task. Again, use some sort of stopwatch or time device. And so that's the nature of this data, where we actually handle numbers. Well, we can go ahead and perform calculations with those numbers, like the average. And I'm sure you've all done something like that in some of your math classes, where you calculated means and so forth. And that's essentially what we're going to be doing with those numbers, only adding on to those processes. Oh, excuse me here. Got allergies acting up. Those numbers can be broken down into two different types, continuous and discrete. And the discrete nature is basically numbers that, again, would be, let's say, positive integers. How many times do you do this? Once, twice, three. How many kids do you have in your family? 1, 2, 3, 4, 0, whatever. You can't have 1.2 kids or something like that. Whereas a continuous variable, for a subject might be something along the lines of how tall you are. And if we had an instrument, accurate enough to go to 10 million decimal places, theoretically, there could be infinitely many heights. So we treat that as a continuous variable that can take on all values. If there were heights, X could be anywhere from, like I said, I don't know what the smallest human being is. Yeah, I guess you have to look in the human or Guinness World Book of Records. But let's say an inch or something like that, or whatever, up to 14 feet tall or something. Well, there's infinitely numbers between 1 and 1 inch and however many inches are in 14 feet and so forth. So we will treat numbers that can take on any value a little bit differently than the ones that, again, we are just like counting numbers, 1, 2, 3, 4, and so forth. So we use this word distribution. Okay, and you'll be encountering that. And again, distribution of a variable, whether it's a person's height, a person's weight, the number of people in their family, their favorite color, who they're going to vote for, that variable. We want to know what the distribution is. And the distribution is basically what values that the variable takes and how often it takes these values, takes on these values. All right. And so, we have the quantitative data, all right, where we're going to, again, do some sort of graph to kind of summarize those data and then calculate measures of center and spread. What's a typical value and how those values are spread out. And we'll talk about the numbers that we use to measure those. And, you're not going to probably have to do this. You'll just do components of it because Alex kind of guides you through some things. But this was kind of a mnemonic device. These are the things that we want to measure or comment on, the shape of that distribution, the outliers, if there are any, the center of them, and how the data is spread out. So we refer to that as SOCS, SOCS. Okay. And, I don't know how much, again, this is the first time I've been through this particular Alex setup, and how much they're going to focus on context. But usually they, in the questions, they have phrases and you just fill in the numbers, but no, they'll take care of the context of what the numbers represent for you. As far as the qualitative data or the categorical data, again, we're going to make the appropriate graphs for those, and then again, write up a distribution, in context. And, again, usually we're comparing counts or percentages. Okay. So as we move on here to this next slide here, this is an example. Let's say, for instance, we had, a bunch of, we wanted to do a survey and just kind of keep track of types of stations on the radios. Okay. And I don't know, this is an example I grabbed from somewhere. And excuse, like, some of this stuff here, these categories kind of got ran together here. I'll show you, there's a software that we're going to be using, or I'll use to at least illustrate some things. You're more than welcome to use it. It's free web-based software. It's Staplet. Okay, and just type in staplet.com and you'll get it. And it's kind of a nifty little software package. And but anyway, this would be, again, the frequency distribution. If you count it up, just again, well, what type of radio station are they? Well, are they adult, contemporary, adult standard, contemporary hits, country hits, news, talk, info, oldies, so forth. All these categories here, thus the term categorical variable, and we just basically count up. So this is a frequency distribution. It tells you how often these values come up. What values are there? If X is the type of station it is, again, your response is just one of these words. And so we count the number of times those come up. And we can, express those in either a bar graph, which I'm sure you've all seen before. And like I said, a lot of these are running together here. And you have a lot of different categories. Sometimes that happens. Or you can express it in a pie graph. Okay. And so, I'll kind of show you a little bit later how to make this stuff here. So this would be the, again, the way that you go about with the frequency distribution. You just enter in the variable value and then how many times it pops up, and then it'll give you the statistics, which again is just repeating what you typed in, but also it'll convert it to a percentage. Okay, so you could see that, again, if you took this 1,556 and divided it by the sum of all of these, you're going to get about 11.2% of those. Okay. And so, but with the graph, it's kind of nice. You can identify the ones that are most popular. And if these weren't all run together here like this, but, you would see that, country, religious, and news talk are the, three tallest bars, and then, others probably kind of close up there with those as well. But you could, kind of just look and get the visual effect here to see that. And also that's true with the pie graph here. Again, you can see the biggest pieces of pie are the green with news talk, and the red, which is religious, and the blue, adult contemporary. Okay. So that's, some of the stuff that we're going to be doing again. And, that's what you see there for categorical variables. As far as the numerical variables, okay, or the quantitative, you've all done this before, and you're going to get, this is just an old slide that I had, but what I wanted to do is just show you, the mean. What it is basically, if you add up all the values here, and this is just a little scenario about, 15 workers and how far they travel, how much are how many minutes it takes for them to get to their job, how much time do they spend traveling. And so, we have here 15 subjects, and these are all the times here. And so I have all this exposed. I don't think this is Excel. I know we'll be using Excel a little bit in this course, a fair amount. And basically what it does is just adds all these things up here, and we get the total count, and then we divide by the total number of data points. So if we add all that up, it adds up to 337 divided by 15, and there you go. You can see here, I kind of show the formulas of how those work. You can type this in a spreadsheet, the sum of, B4, which are these cells here. I don't have the headings on here, but this would be the fourth row in the second column, B4, and just add up all of those and then divide by 15, or I can put in there, put in the count for that, and that 15 will be automatically computed. Or there's just something like an average command, and they all produce the same thing. And essentially, you'll see this summation notation where basically these are all the x's, so to speak. This is x sub 1, x sub 2. So as I goes from 1 to 15 here in this case, x sub 1 is just the 30, x sub 2. So all this is doing is representing adding all these numbers up. That's just a mathematical way of doing it. And the symbol, again, is this x with a little flat bar over top of it. We'll literally call that x bar, and that represents the mean, okay, of this set of numbers. And obviously, I didn't ask every worker in North Carolina. There are obviously a lot more than 15. So, again, in terminology we'll be working with, this would be a sample, and if it was collected in a proper way, then we could maybe make some sort of argument this would be representative of all people in North Carolina, but we're not really sure about that. So, oh yeah, no, it does. It says they did take a random sample by the Census Bureau, so that would have been something that we could probably check on. Notice this graph here, we'll go over, what a dot plot is, but basically it's putting a dot over every number that we observe. And so somewhere along here, we should see 4 tens in here because there are 4 dots stacked up on the tens and so forth. And again, just gives you a visual summary of what's going on here. And we can see that we have one extreme value of 60 minutes out here, but most of them are right around down here, and they kind of spread out a little bit to the right. Okay, and we'll talk a little more about that when we get into the graph. So that's what the mean is. The standard deviation, and I know this is quick because it's just, we're not going to get into that much of the interpretation. But again, I kept up here the mean stuff here. And what the standard deviation is, it's kind of a scary looking formula. But if you look at the essence of it, what we're doing is we're taking each observation and subtracting a mean. This little thing right here is a deviation. We take the observation. So if I know my mean is 22.47, my first deviation is going to be 22.47 minus 30. Then my next deviation is going to be 20 minus 22.7. Okay. I think I said that backwards. That should be 30 minus 22.7. And then the next one is 20 minus 22.7. The next one's 10 minus 22.7. Now you notice here, just in these 3 numbers, the first one, if I take the observation and subtract the mean, it's going to be positive, but the other 2 are negative. So if I did this in the spreadsheet, did that for all of these, here are all these differences. And notice what happens, it kind of makes sense. Well, if I want to know what the average, what the spread is, I'll just find the average deviation. But the problem with just adding up the deviations, just adding these up and then dividing by the number of things that I have, is that the deviations are always going to add up to 0 for every single data set when you take and subtract the means and calculate them in this manner. So I don't care what these numbers are. If I calculate the mean of them and subtract the mean from each one of those and find the deviation for each data point, add them all up, they're going to cancel each other out. And if we go back to this reason that happens, probably the best, easiest way to describe it, if my mean is 22.47, which is right about here, if you look at this as a seesaw or balancing right on that fulcrum of 22.47, it's a balance point. All right, so they're going to kind of equal out one another, and it would remain at equilibrium there. And those deviations always have that characteristic, okay, for any data set. So what we're going to do then is take each of the deviations and square them and add up all the square deviations. And that's what this represents here. Okay, so notice I take a deviation here, subtract the mean, square it. Take another observation, subtract the mean, square it. Take another one, observation, subtract, and then I add all these up. That's what I'm going to do. And then I divide by n minus 1. Now, this is another thing that's kind of a little bit weird, but the bottom line is why we're saying n minus 1 is that 14 of these things can deviate or vary freely until the and the last one would be predetermined. So if I knew all the deviations added up to here, whatever 12.747, then I know the next one has to be negative 12.47 because the deviations always add up to 0. So you could do that with anyone. If I take this deviation here and I add up all the other ones, I would get them to add up to negative 2.53. If you want to try it, go ahead. It would happen. And then when I add 2.53, then I would get 0. So this number is like determined. I would know this number as long as I know what 14 of these things add up to. I'm always going to know the 15th. That's what a degree of freedom is. So there's 14 degrees of freedom. So to adjust for that, we divide by n minus 1. So really what we're doing is we're actually taking, in essence, the average square deviation. Okay. Remember, a deviation is basically essentially how far a data point is away from the mean. So if I take the average square deviation, all right, and I take the square root of it, that's going to give me my average deviation. Okay. So that's basically what we're getting here. So if I just take the square root of this number here, I get 15.23. And so what we're saying is that on average, each one of these observations is about 15.23 away from the mean. That's what a standard deviation is. Okay. And then later on, we'll get into, applying a little bit more what we can use the standard deviation for. But let's right now leave it at that a standard deviation is on average how far a data point is going to be away from the mean. Okay. So we'll get into some specific ALEKS questions where you may have to interpret that a little bit, and hopefully this little discussion helped with that. I'm going to try to get through some of this other stuff a little bit quicker to keep this video reasonable length. But here again, the same group of data. Another way of measuring center and spread is this 5-number summary, which we're going to call minimum, maximum, pretty obvious, 5 and 60. The median, and we get the median by basically putting them all in order and taking the middle value, okay, which is 20 right here, and that would be the median. And then the Q1, or sometimes called the first quartile, is the median or the middle of the lower half of data, and the third quartile is the median of the upper. And so you think the word quartile, quart means 4. We're breaking up into 4 parts: first quartile, second quartile, third quartile, fourth quartile. Okay. And so, when you get into reading about percentiles and all that sort of stuff, again, it's just how things rank relative to one another when we list them from highest to lowest. So again, you can see that this applies for the quantitative variable. Okay. So that's how you do this. And again, software is going to be doing that for you. So there's, but yeah, I want you to understand what those numbers represent that are getting spit out on the spreadsheet or a calculator. Okay. How do we graph quantitative data? There's basically 3 types of graphs: histogram, box plot, and dot plot. I'll show you real quickly how those, and your ALEKS is mainly going to focus on these first 2, and probably more on the histogram than any of the box plot. The dot plot I just kind of threw in there because, again, it's just another way that sometimes I don't even want to say becoming more popular, but you'll see it from time to time. When we make this graph, this is a histogram. We'll get into that. We talk about shapes of them. And first one here, symmetric, where we, basically think, if you go right down the balance point and there's some characteristics of what the mean, median, and mode is the one that occurs most often, but all those things would be the same value because it's typically balanced on the left and right. The data is evenly dispersed on both sides. When we start tailing off to one direction, we call that skewness. All right. So we're going to call this right skewed. Sometimes they use the word positively skewed, and this is just from your textbook. So if the tail goes to the right, we say it's skewed right. And if the tail kind of goes off to the left, and what we mean by tail is just that little skinny part that kind of fades away here, we would say tail left here means skewed left. Okay, so those will be the shapes. So here's an example of what that Statplet does. And you can see that I put the same data set in here and basically produced a dot plot. Okay, so it's going to be as simple as typing the numbers in here and selecting what graph. Notice the summary statistics are produced here, and notice it calculated the mean and standard deviation, which I showed you on the spreadsheet. So like I said, the software is going to be doing this stuff for you here. And it also is the 5-number summary, which is kind of nifty. Okay, so all that stuff pops up here for you. When you click this, and I'll show it to you live here because I do have this up in one of the tabs in Chrome here. You just pull on the pull down menu, select histogram, and it'll automatically go ahead and show you a histogram here. Okay, which I'll get in a little more detail when I get in the live version here. But again, what we do is break this up in classes from 0 to 10 here. We see that we have 1 observation in there. From 10 to 20, we have 6 and so forth. And I'll show you how we do the cutoffs here in a second. All right, and we have some ways of changing this, and I'll show you that again in a live vision. And then we use the 5-number summary here, the min, the max, the median, third quartile, first quartile, to find 5 points here on this graph. And then what we do is we make this box plot. So all we do is just make, the line down the median, do a line down Q1 and Q3, connect those, make that into a box, and then extend out. Sometimes these are called box and whisker plots, or these are whiskers, so to speak. And what you do is you kind of get, again, a visual of what's going on with the data. And we see that this, upper 25% of the data is really spread out. We see where the middle 50% of the data, or, the next highest 25%, okay, or the third quartile, second quartile, and so forth. But we see there's much more variation in the upper values than we do in the lower values. Okay, and again, gives us that visual sense to it. And that's what a box plot is. Okay. So how do we do that? Well, again, what we do is first we type all these numbers in. Now, this is the live version, so you can see my cursors in there. I don't want to mess all these up. But if I would do that, if I set reset everything, then it's going to kind of erase it. And I don't think you want to see me type these in again. But here's what I'm talking about is that you can just put your cursor over top of this and you see there was 1 observation that was greater than or equal to 0, but less than 10. So you're including the left point, but not the right end point of that interval here. And then in the next one here, all values 10 or above, but less than 20, there were 6 of them. And then the next class here, and we refer to these as classes. You'll see that as you go through the material. We see we have 30 in that class, and then, or I'm sorry, 3 in that class, and then 2, and then finally the 1 observation. We knew there was that little 60 out there, right? There was only 160 or 1 value between 60 and including 60, but less than 70. And, all I had to do here is, again, just to convert it back to that, I can just, choose dot plot. I can choose whatever I want, histogram, box plot. I can go back and forth from these things quite easily. We're going to get into some of this other stuff later on with Statplet to illustrate some concepts, but we won't right now. But you can see that, again, those summary statistics are included there. Okay. Now you're going to be doing some of these when you see in the ALEKS calculator, it's able to do some of this stuff. And usually the things that you need to do to answer the questions can be done in there. All right. So we'll show you that, in those other videos. But again, I'm trying to wrap this one up. I got a couple more slides here for you. This kind of leads into what ALEKS would do. Here's, again, just a histogram. And notice they gave you some boundaries here for these values. And notice they didn't do the greater than or less than here. And this is kind of what ALEKS will do. It'll kind of give you these. You don't have to figure these out on your own, but you'll have to go through and figure, count up. And it has a way of sorting them to make it a little bit quicker and not so many numbers. But if I did take the time to figure out the number of observations in each of these intervals, I would get the 2 and 8 and 18 and so forth, and that would determine the height of those bars. Okay. So again, this is just from your textbook here, but I just wanted to, again, show that to you. Okay. So with that said, I think there was, yeah, so if I get down here to this next one here, okay, so, again, this is just, again, summarizing what we just did there, in terms of how to describe and interpret quantitative and categorical or qualitative data. And, the one last thing I wanted to talk about was the data production. I'll do a couple of the problems. We don't spend a lot of time talking about it in this course. I know when I taught AP Stats and other stats courses, we spent a good deal of time on this, but where do we get our data from? And typically we're going to collect it, with surveys or measuring methods. And so we call that sampling, okay? Or we conduct experiments. We'll get subjects that, typically volunteer. We're not going to get in all the ethics stuff, but there's a very ethical way of getting people to, participate in experiments and, how do we ethically use, animals and all sorts of stuff. There's a lot to this, but we're not going to get into much of it. But what you have to remember is that, again, we're looking at getting data that represents, a small group of people or individuals that represent a larger group, so that when the measurements we get from them can represent the larger group, okay, the ones that we can analyze and measure. And so we talk about this sampling error, where there's always going to be some sort of error, right? We're not getting all the data. And that's what sampling error is it's just, every time we get a different sample, we'll probably get different results. If I ask people what their shoe sizes were and I ask 20 people and I get an average of, I don't know, 9.2, and maybe the next time I get an average of 9.7, just because they're different and I didn't ask everybody. Okay. So this is kind of the good type of error. We're going to be able to measure this based on probability. This is the bad type, the non-sampling error. And a good example of that would be to ask a bunch of people who they're going to vote for. And if you go up and ask the people after a Trump rally or something and only ask them, obviously that's going to be biased. There's going to be systematic outcomes because they were just all at a Trump rally. So, we call that non-sampling error when there's, again, data that has, some sort of systematic outcome that's going to make it non-representative of the entire group that we want to, ask questions about or answer questions or solve problems. Okay. And so the remedy is always this is the best thing that we could do, is do a random sample in which the sample with all members of the population have an equal chance of being selected. This is one definition of it. So if everybody has an equal chance of being selected, then really we have an equal chance of selecting all possible samples of a certain size. And that's technically the definition of a random sample, but we'll just go with what your book's saying here. And so the result of that is that every person or subject or object or whatever it is that we're measuring has equal chance of being selected. Therefore, it's in the long run is going to be very representative or a good representative. We have some anomalies, but they don't, happen very often. And that's where we get into using this probability with this sampling error. Okay, so with this idea, in all practical purposes, it's logistically impossible to conduct random samples. And how it has to be done is, you number each individual, and just doing that and giving everybody a number, so to speak, 1 through I don't know how many millions of people, 300 million people here in our country, and then you randomly select numbers, and that would determine who's in the sample. Well, again, that's logistically a very difficult task. So we have other methods of sampling that I think we'll look at briefly. They're highlighted more in your textbook here. If I just pull that in real quick, this idea of, if I go back, I think it's in chapter 1, yeah. Systematic sampling, stratified sampling, cluster sampling. And a lot of times really what we do is we kind of combine these into multi-stages. And that's kind of how all the polling companies do this, and ways of getting data. The result is very close to random, and it still uses probability to select the individuals, okay, or chance to select them. But it's usually, again, combining all of these, which again, this course doesn't get into that too much, but, we're going to assume a lot of things that we do are just, essentially a random sample. Okay. But again, I just wanted to mention practically, that's very difficult to do. And just to show you how complex it is, I know when I was in graduate school, I took a course on sampling methods, and that was the whole semester, and that's all it was. So, so there you have it. I know that's kind of a bit longer than what I wanted to do, but there's your introduction. Obviously, you're going to see here in this announcement, there are other videos below, which you probably will be a little more interested in, because those are going to be specific examples on how to do specific ALEKS problems. However, I think it's a good idea. Hopefully you were patient enough to listen to this entire video, because what it did do is give you a good overview of not only the course, but again, the first section of the course that we're going to be talking about. So, all right, enough rambling for me. Hope that helps, and we'll see you next video.